What we want to do is two things, really. First of all, to discourage the long-term parker in the streets of London. I've always said that if there's a place available in the street for parking, it should be used by 8 chaps for 1 hour a day rather than one person for 8 hours a day.
The supporters of parking meters say they help regulate parking by limiting the amount of time any one car can stay at the meter. They share out the available space more fairly. But of course, they also provide money for the local authorities' coffers. Take this meter. It takes 20 pence an hour. It works from 8:30 in the morning till 6:30 in the evening. That's 10 hours a day. And if it's fully used, and most of them around here seem to be, that's £2 a day. The trouble is, sometimes parking meters break down. They get jammed, or parts wear out, or it's even known for water to get into the works. That's great for the motorist. He or she parks for nothing, but not so good for the local authority, because they lose the £2 while the meter's out of action for a day. So what's the solution? Well, they have to employ repairmen who take off the head, that's the works of the meter, and take it back to the depot for repair. But the question is, just how many repairmen do they need to employ? Too many, and they lose money by paying more wages than they need. Too few, and they again lose money by having too many meters out of action. So what they want to know is just where is the happy medium between these two.
What is the happy medium? How do you balance repair costs against revenue lost? That's a difficult question because in a very real sense the answer's uncertain. Just how many meters are going to break down next week? When is this meter going to break down next? We don't know. Sooner or later it'll break down because it's mechanical, and most mechanical devices break down every so often. But how often? What's the chance that it'll break down today? Is this very likely to happen, very unlikely, or somewhere in between? Somehow we've got to quantify our ideas to put a figure to the chance of a meter breaking down. A high figure if it's likely to happen, a low figure if it's unlikely. It's this measure of chance that we call probability.
Now, what exactly is meant by the probability that this meter will break down in the next 24 hours? You might not know how to go about answering a question like that, but suppose I asked you this question instead. Here's a die. It's a perfectly ordinary die with 6 faces. If I roll it, what's the chance of getting, say, a 3? You can probably answer that. It's 1 chance in 6. But why would you say that? One argument is that there are 6 faces altogether, and no particular reason why one face should turn up rather than another. You'd feel that they were equally likely, and so the chance of any face turning up is 1 in 6. But there's another reason for saying the chance is 1 in 6. A 5. Well, that's not a 3, but that's just 1 throw. You can't tell very much from just a single throw. Let's try a few more. A 1. We'll record the result of each throw at the bottom of the screen. We've had a 5 and a 1, and now a 6, and another 6, a 5, and 1. So we've had 6 throws, and none of them were 3s. Does this mean the chance of getting a 3 is 0? Obviously not. We've only had a small number of throws. 6 throws aren't really enough to understand fully what's going on. I'll roll this die several more times, But now we'll plot a chart recording the proportion of threes that are thrown. 5, 3, 4, 4, 4, 1, 5, 1, 2,
5, 5, 6, 2, 1, 4, 3, 3, 6, 4, 5, 6, 3, 3, 3, 6, 4, 5, 4, 1, 1, 3, 1, 4, 3, 6, 2, 1, 5, 2, 6, 4, 1, 1, 3, 6, 6, 4, 4, 6, 6, 6, 5, 1, 6.
That's 60 throws in all, and we've had 9 threes. 9 out of 60. That's a proportion of 0.15. So should we say that there are 9 chances in 60 of getting a 3? Well, if we threw the die another 60 times, we might get 11 threes. And yet again, we might get 8 threes. There's still uncertainty in the result. But you'd be very surprised if we got 60 threes, or 1, or no threes. And that's a feature of chance. You can't make definite predictions, but you can say what's likely or unlikely to happen. This is because you can identify patterns in repetitions of chance events. And perhaps the most important pattern of all is the one which this graph is showing us. If you look at this graph, you can see large fluctuations on the left and a tendency to settle down on the right. Now, what does that mean? It means that if you have some chance event, like observing a 3 when you throw a die, and you repeat that experiment time and time again, then the proportion of times the event happens gradually settles down. And the more the number of throws increases, the steadier this proportion becomes. It's this limiting proportion we're going to call the probability of the event happening. With this die and the event of getting a 3, we've achieved a proportion of 0.15 after 60 throws. That's 9 in 60. But if we continued, after 600 throws, we'd be surprised to get a figure as low as 90. And with 6,000 throws, we'd be extremely surprised to get a figure as low as 900. We'd expect something much closer to 1,000. And that's what actually happens. Before the program, we rolled this die 750 times. It took us just over an hour, and this is the result we got. Once again, this graph shows the proportion of threes. It zigzags wildly to start with, still zigzags after 60 throws, but after 300, it's getting quite smooth. And by 700, it has settled down to a value very close to 1/6. And that's what we mean when we say that the probability of getting a 3 is about 1/6.
Now we've got the idea of probability, but how does that help us with parking meters? If we know that in the long run, this parking meter worked 5 days out of 6 on average and broke down 1 day out of 6, then we'd say that the probability of its breaking down was 1/6. In fact, we do have some information about parking meter breakdowns from a number of cities up and down the country. Records show that the probability of a meter breaking down in a day is nowhere near 1/6. It's much more like 1/60th. And now we're in a position to pose our problem. Another city somewhere in Britain wants to install this same kind of parking meter. They want to install 2,400 of them. Suppose the probability of a meter breaking down in a day is 1/60th. Then how many meters will we need to repair a day? Seems straightforward enough. 2,400 meters and a probability of 1/60th. You just multiply those figures together and get 40. So on average, 40 meters a day will break down. And one might think that that's the repair capacity one needs. In other words, enough men to repair 40 metres each day. That's just what we would need if breakdowns occurred regularly like clockwork. 40 metres Monday, 40 Tuesday, 40 Wednesday, and so on. But things aren't as simple as that. Breakdowns occur in an irregular pattern. What is this pattern? To get an idea of what it's like, we are going to introduce a technique called simulation.
This is our basic building block for simulation. If you have an activity with an uncertain outcome and you can't perform it lots of times, you can pretend to perform it by rolling the die instead and using the result to represent the outcome of the activity. For example, the behaviour of a parking meter. Of course, things might not be as straightforward as that. When you roll a die, there are 6 possible outcomes, each with probability 1/6. But with the parking meters, there are only 2 possibilities. Either a meter breaks down or it doesn't, and it breaks down with probability 1/60. So we have to amend things slightly by redefining our die. Here's a way of doing that. This die has 60 faces, and one of them is singled out. It's painted yellow. If I roll the die, then the chance of getting the yellow face is 1 in 60. So if I choose the yellow face to represent a breakdown, over a long run, about a 60th of the throws will produce breakdowns. That's not the yellow face, so the meter continues working. And the same again. But it's a bit unwieldy having to get a special die and rolling it thousands of times. There are other, more practical methods, one of which is to use a computer. The computer's generating these numbers at random. Each number is between 0 and 1, and there's no reason why any one number should appear rather than any other. Any number is as likely as any other. So how can we use this for our simulation, where the probability of a breakdown is 1/60? Since all the numbers are equally likely, let's say that if the number is less than 0.016, it'll represent a breakdown. Otherwise, if it's greater than or equal to 0.016, it'll represent the meter continuing to work. So this number, less than 0.016, represents a breakdown. And the numbers you saw leading up to it represent the meter continuing to work. The probability of a breakdown is just 0.016, or about a 60th. So now we can use the computer to simulate our parking meter problem and discover what is the optimum repair capacity. Here's our first meter and our first random number. The number's greater than 0.016, so there's no breakdown. The second meter, again no breakdown. And the third, but this time the random number's less than 0.016, so this meter breaks down. We could do this for all 2,400 meters. And here you see we've got a total of 43 breakdowns. That's slightly higher than average. We expected 40. But that's a simulation for just one day's operation. Let's try the simulation again for a second day. 29 breakdowns, this time below the expected value. And the third day. 48 breakdowns now, again above the value expected. So we're getting a sequence of numbers, 43, 29, 48, and so on, which tell us how many meters break down from day to day, using our assumption about the probability of a breakdown to a single meter on any one day. Now, the average number of breakdowns is 40, and the question we want to ask is, would a repair capacity of 40 still be adequate in the light of the variability we've just seen? We can try to answer this question by continuing our simulation. The computer's been programmed to work out the number of meters that break down each day. And if I set it going, we'll see the results. So there's certainly considerable variability. 30s, 40s, 50s, and there's a 28. But it's not easy to see from these numbers just what pattern the variability possesses. We can get a better idea of this by building up a histogram. We'll plot the number of breakdowns along the bottom, 0 up to 60. And then vertically, we'll show the number of times that many meters break down. On the first day, 43 break down. So we'll draw a rectangle in the column for 43. And we'll record the number of days in the top left-hand corner of the screen. On the second day, 29 meters break down. Let's plot that too. And on the third day, 48. If we continue the simulation for 300 days, that's a year's worth of data, we'll get an idea of what the picture looks like. The number that's come up most often so far is 37, but many other values are possible. The lowest we've got is 24, and the highest 63. So there's quite a range of values. But would we get a similar pattern if we looked at another year's observations, or at an even longer run? Would the pattern settle down? We saw that for the die, when we looked at the proportion of threes thrown, it did seem to settle down. So let's do a similar thing for the parking meters by plotting a histogram of proportions. We'll go back to when 100 days had passed. The histogram looks the same as before, but now the vertical axis gives the proportions of times that, for instance, 38, 39 or 40 meters break down, rather than the absolute counts. Now let's continue the simulation. At first, the changes in the pattern are quite noticeable. But as the number of days increases, we can see the fluctuations are getting smaller and smaller.
So it might seem as if our first simple estimate of 40 meters a day was right, and this repair capacity would do the trick. But will it? After all, quite a lot of days have more than 40 breakdowns. Some days will have as many as 49 or 50 or more. So those days will generate a backlog, maybe 9 or 10 meters that weren't repaired that day. And then there are days with less than 40 breakdowns. Some days have 30 or less. And on those days, the repairmen have a chance to clear the backlog. Now, just how fast will the backlog be cleared?
Let's plot another diagram. This time, it will be a day-by-day diagram, showing the number of meters breaking down each day. We'll assume that any broken meter is out of action for a whole number of days at a time. Now let's see how the repairs are managed. Underneath, we'll plot the backlog. Clearly, the repairmen are being overwhelmed. The backlog's growing larger and larger. But why? On days when the number of meters breaking down is greater than average, the backlog builds up. Later on, when there are fewer than average breaking down, the repairmen are able to clear the backlog, at least to some extent. So we clearly need a greater repair capacity than 40. But how much greater? If we chose 50 or 60, then we would certainly eliminate any backlog very quickly. But of course, increasing the repair capacity is expensive. We don't want to make it unnecessarily high. So how high should it be? Let's return to our simulation. We'll try a repair capacity of 41 meters a day. now 42, and 43, 44, and finally 45. As you'd expect, increasing the repair capacity reduces the backlog, saving revenue. But it also costs money in terms of the repair team's wages. Somewhere there's a balance where the money saved in revenue just matches the extra cost of the increased repair capacity. And that's something we can work out. At current rates, the cost of increasing the repair capacity by 1 metre a day is equal to the revenue from about 1.2 metres in a day. So if repairing an extra 1 metre a day reduces the backlog by more than 1.2 metres a day on average, there will be a net saving in cost. For example, going from a repair capacity of 40 metres to 41 reduces the average backlog by about 27 metres a day, much greater than 1.2, and so obviously worthwhile. From 41 to 42, the backlog is reduced by just over 6 metres a day, still worthwhile. 42 to 43 by 2.3 metres a day, less than before, but still worthwhile. 43 to 44 by 1.2, and as we said, this is just the break-even figure. So as far as cost is concerned, the authority could choose either 43 or 44. But of course it may have other reasons for choosing one figure rather than the other.
And that seems quite successful. We've used probability to get definite results about an uncertain situation. Although there's variability in the breakdowns of parking meters, we've come to grips with it by using the concept of probability as a long-term proportion of breakdowns. And we've used the tool of simulation to see what pattern of breakdowns is likely to happen. But there are still some questions you might be asking yourself, in particular about the simulation. We've run it once and got an answer to our question, but we know that there's variability. If we ran our simulation again, would we get the same answer? What's the risk, for example, that when it came to putting things into practice, the authority might get a long run of bad luck and an enormous backlog, even with our recommended choice of repair capacity? Now, these are questions which start to build on the theoretical ideas of probability. We'll be dealing with these questions in the rest of the course.